Let's see how to construct a digital signature scheme based on the generalized discrete logarithm problem. Previously, we explored key generation, encryption, and decryption. In key generation, we considered a generator for a finite cyclic group. This generator is denoted by little g. The finite cyclic group is denoted by big G. This generator is an element of this group. We also chose a secret value S0 from the set denoted by big S. From this set denoted by big S, we will choose all of the secret values. The secret value S0 and the generator G were used to define the public value P0. This public value P0 was included in the public key. In the secret key, we included the secret value S0. So key generation results in a pair of keys. We have the public key, which is sent through a public channel, and we also have this secret key, and that is kept secret. There is some additional information in these keys. We have some contextual information. So we specify the group that we're working with and also the set that we're choosing these secret values from. In addition, we specify the generator. So this generator will be used to define other values. In the secret key, we have to include the secret value S0. And in the public key, we have to include the public value P0. So in asymmetric encryption, or public key encryption, this public key gets broadcast through a public channel, and then another participant can use the public key to encrypt a message. So a message is encrypted using the public key, and that produces the ciphertext. The ciphertext is then sent through the public channel, and the ciphertext can be decrypted. So that means we turn the ciphertext into the message. That can only be done with the secret key. So the secret key is used to turn the ciphertext into the message, and that is done in the decryption procedure. So the secret key is used for decryption, and the public key is used for encryption. In the digital signature scheme, we're going to replace encryption and decryption with signing and verification. We're going to use the secret key to sign a message. Then we're going to send the signed message through this public channel. Then another participant, we can refer to as the verifier. This verifier will use the public key to verify the signature on that message. So we have this participant that is generating the keys and signing the message, and then we have another participant that is verifying the signature. And these participants are communicating through a public channel. So let's have a look at the mathematics, and let's see how to construct this digital signature scheme. So after key generation, we're going to use the secret key to sign a message. So we're going to have message signing. Message signing will involve choosing a secret value, S1. We're going to choose that secret value from the set denoted by big S. So that's the same set that we chose S0 from. So from this set, we're going to choose S0 in key generation, and we're going to choose S1 in the signing procedure. Then we're going to use this secret value S1 to define the value W. And W is defined as the generator raised to the power of S1. So we're using the generator and the secret value to define this value. And that's very similar to how we defined the public value P0. So we have this generator and we're raising it to the power of a secret value. And now that we have this value W, we're going to define the value H. Now H is the hash of the message, which we are signing, concatenated with W. So this symbol over here means concatenation. We're concatenating the message with this value of W that we've computed using the generator and the secret value S1. And this capital H is denoting a hashing function. So we are hashing the message concatenated with W, and we're using that value to define H. And now we're also going to define a value Z. Z is defined as S1 plus or minus, depending on the convention choice, H times S0. S0 has come from the secret key. So the secret key has included the generator and this secret value over here. And S0 is then being used to define Z. So we have two secret values that we're working with. One of those secret values came from the secret key, and another secret value was generated in the signing procedure. So S1 is used to define W, which is then used to define H, and then H makes its way over here into Z. So Z is this secret value S1 plus or minus H times S0. And this is a convention choice. We can pick either plus or minus over here. So H and Z are collectively the signature for this message. So now we have enough information to construct the signed message. And we're going to send that information through the public channel. So this is going through the public channel. We're going to have the signed message SM. The signed message includes the message, which is going into this hash over here. And then we have to include Z and H. So these values, Z and H, we can collectively refer to them as the signature. So we have a message and the signature. So together, that is the signed message. Now, the verifier, who is the other participant over here, can use the public key to verify this signed message. So let's see how verification is going to work. So we're going to have verification over here. Let's define U as G to the power of Z, so that's this Z over here, times P0 to the power of minus plus H. So here we have minus plus, that's the opposite sign to the sign that we have over here. So this is a convention choice. Here we have plus minus, and then over here we have minus plus. As long as the signs are opposite, this will work. So this times symbol over here does not have to be multiplication. The times symbol is just the symbol that we're using to denote the group operation. So that's this group over here, denoted by big G. That group has an operation, and we're denoting it with this times symbol. And this exponential notation, that is used to denote repeated application of the group operation. So we have the generator raised to the power of Z times P0 raised to the power of minus plus H. G and P0 both came in the public key. So these guys have come from the public key. But the signed message has included this signature, which includes Z and H. And Z appears over here and H appears over here. So this value of U is being defined in terms of values that have come from the public key and values that have come from the signature. Now let's define the value V. So V will be defined analogously to H. So V will be the hash of the message concatenated with U. So we don't have W over here. Instead, we have U. And to perform verification, we're going to check whether V is equal to H. So V is computed with this message. So we take the message from the signed message, and we have U. And U was computed with information from the signature and the public key. And the verification procedure involves checking the equivalence of these two values. Now, if V is equal to H, then we have a valid signature. Let's see why this works. So we're going to do some algebra, and we're going to see why U and W are actually the same value, assuming that this is a valid signature. So W is equal to u because we can rewrite this in a different form. So u can be written as g to the power of z, but what is z? Z is s1 plus or minus h times s0. And then we times by this value over here, p0 raised to the power of minus plus h. What is p0? P0 can be written in terms of the generator. So we have the generator to the power of s0. And that is being raised to the power of minus plus h. So this definition is present up here. So we're raising the generator to the power of s0. That's this secret value that was chosen in the key generation procedure. So that's what we're dealing with over here. So this is just a different way of expressing this definition of u. And now we can group these terms together because they share the same base. And that's going to give us g to the power of s1 plus or minus h s0. So that's what we have over here. And then we're going to have minus plus h s0. So that's come from these terms over here. So that we have opposite signs. So it doesn't matter which convention choice we have, as long as the signs are opposite, there's going to be a cancellation over here. So we can write this as a cancellation. So these two terms will give 0. And then we're just going to be left with the generator to the power of s1. But that is the definition of w. So we have w over here. And that shows why u and w are the same. So we have an equivalent value. And we are concatenating that value with the message and then putting it into this hashing function. And that's giving us h over here and v over here. Now, assuming that we have a valid signature for this message, the public key has enough information for us to verify the validity of that signature. And we can do that by putting it into this hashing function. And because u and w are the same, they're going to produce the same value. That is this h over here and this v over here. So they will be equivalent. But if somebody else tries to create a fake signature, then this was not going to work. You're going to have different values for w and u. So when you put them into these hashing functions, after concatenating with the message, you're going to get different values. So this is not going to be equivalent. So this is how we perform verification. Now, I want to clarify some notation, and also I want to specify the basis of this entire digital signature scheme. So this is based on the generalized discrete logarithm. Now, the notation that we're using over here is exponential notation. So we're treating this like it's a multiplicative group, but it does not have to be a multiplicative group. This group operation could be something else. So let's just have a look at what this notation actually means. So if we have the generator g, and we use the group operation denoted by this times symbol to combine it with g repeatedly, and we keep on doing this, and we do this s times, we have s copies that are being combined using the group operation, we can denote that as g to the power of s. So this exponentiation notation is actually telling us that we have to use the group operation s times. And we're just combining the generator s times using the group operation. So that's what we have over here. And this is the value that we're going to send out through the public channel. So this, we're going to consider the public value p. So we have g to the power of s is equal to p. But we could write another format for this equation. We could write it in terms of s. So we can consider s the logarithm base g of p. So we can think of this as a discrete logarithm. Now, this notation may be a little bit deceptive. That's because we're not dealing with logarithms that we encounter in school. We're dealing with a far more general type of logarithm. This is the discrete logarithm. And we're also not necessarily just dealing with integers and multiplication of integers. We're dealing with a far more general type of cyclic group. So the operation over here does not have to be multiplication. It could be addition, or it might be some even more complicated group operation, some more complicated way of combining these group elements. But this notation is useful to have because we can make the analogy between this type of operation, and we can also connect that to the logarithm of the numbers that we're used to. So this secret value can be thought of as the logarithm base g of the public value. We have generalized this concept of the logarithm. That's why this is called the generalized discrete logarithm problem. So this is a computationally difficult problem on a classical computer. But on a quantum computer, this computational problem is not as difficult. So it's much more easy to do on a quantum computer. So that is actually the reason why we are considering post-quantum cryptography. So post-quantum cryptography is going to provide an alternative so that we don't have to base our digital signature schemes on the computational difficulty of the generalized discrete logarithm problem. So as an overview of this procedure, we have key generation, which produces a secret key and a public key. The public key is broadcast to the public, so that is publicly available. The secret key is used to sign a message, and then the signed message is broadcast to the public. And then the verifier can use the public key to verify the signature of this signed message. So this is how we can construct a digital signature scheme. So we can think of this participant that is signing the message and generating the keys. We can think of that as the prover. And this other participant that is doing verification, we can think of this participant as the verifier. So we have an interaction of the prover and the verifier. In between them sits a public channel. So there's a public channel in between these two participants. And here we have some algebraic working that shows why this verification procedure works.